Hey students, now we discuss one problem for diagonalizing a 3 by 3 matrix. So the question is, diagonalize the 3 by 3 matrix minus 1, 2, minus 2, 2, 4, 1, 2, 1, 4. So the procedure for diagonalizing a matrix is, first we find the eigenvalues and eigenvectors. Then if you form a model matrix X with the eigenvectors are the column vectors, then you construct the inverse of that matrix X as X inverse, and you take the product X inverse AX, and that X inverse AX as the diagonal matrix D with the diagonal entries are eigenvalues of this matrix. So first we find the eigenvalues of this 3 by 3 matrix. The characteristic equation of this matrix is determinant A minus lambda I equal to 0. That is, determinant A minus lambda I is minus 1 minus lambda, 2 minus 2, 2, 4 minus lambda, 1, 2, 1, 4 minus lambda equal to 0. We expand this determinant. We have a minus 1 minus lambda into minus 1 minus lambda into, take the product of these diagonals, that is 4 minus lambda into 4 minus lambda, 4 minus lambda the whole square, minus 1. Minus 2 into 2 into 4 minus lambda, that is 2 into 4 is 8 minus 2 lambda minus 2. 8 minus 2 lambda minus 2. Then last entry is minus 2. So minus 2 into 2 into 1. 2 into 1 is 2 minus 2 into 4 minus lambda. That is 2 minus 2 into 4 is 8 minus 2 lambda minus 2 lambda is plus 2 lambda equal to 0. Simplifying, we got the equation as a cubic equation with the lambda cube minus 7 lambda square plus 7 lambda plus 15 equal to 0. To simplify this equation, and you got the cubic equation as lambda cube minus 7 lambda square plus 7 lambda plus 15 equal to 0. And you solve this cubic equation for values of lambda. Then solve this equation. We have a lambda equal to minus 1 is a root of this equation, because we have a minus 1 the cube is minus 1, minus 7, minus 8, minus 7, minus 15, so plus 15 equal to 0. So lambda equal to minus 1 is the root of this equation. Then dividing this equation throughout with lambda plus 1, we have the second degree equation lambda square minus 8 lambda plus 15. So this cubic equation is lambda plus 1 into lambda square minus 8 lambda plus 15 equal to 0. So solving this equation, we have a lambda plus 1 equal to 0 means lambda equal to minus 1, and this is the second degree equation or a quadratic equation with a sum is minus 8 and product is 15. So the values are minus 3 and minus 5. So the values of lambda are 3 and 5. So the values of lambda for these equations are minus 1, 3, 5. So the eigenvalues are minus 1, 3, 5. So diagonalize this square matrix means we have to construct a diagonal matrix with the diagonal entries are minus 1, 3, 5. So for finding this diagonal matrix, now we calculate the eigenvectors for these eigenvalues minus 1, 3, 5. Also, these eigenvalues minus 1, 3, 5 are distinct eigenvalues. So the diagonalization is applicable for this 3 by 3 matrix. So first we find the eigenvalue for lambda equal to eigenvector for lambda equal to minus 1. For eigenvector for lambda equal to minus 1, we substituting the value of lambda here in this characteristic matrix. We substituting lambda equal to minus 1 here. We have minus 1 plus 1 is 0, 2, minus 2. Zero, 2, minus 2. Then substituting lambda equal to minus 1 in the second row, we have 2. 4 plus 1 is 5, 1, 2, 5, 1, and third row we have a 2, 1, 5. So 2, 5, 1 and 2, 1, 5. So 2, 5, 1, 2, 1, 5 into x1, x2, x3 equal to 0, 0, 0. So for a eigenvector for lambda equal to minus 1, we substituting the lambda value of lambda equal to minus 1 in the characteristic matrix. Then we have a 0, 2, minus 2, 2, 5, 1, 2, 1, 5 into x1, x2, x3 equal to 0, 0, 0. So take the product. The equations are 0 into x1 is 0. So 2x2 minus 2x3 equal to 0. 2x1 plus 5x2 plus x3 is equal to 0. 2x1 plus x2 plus 5x3 is equal to 0. These are our three equations. Then from this equation we find the values of x1, x2 and x3. The first equation is 2x2 minus 2x3 is equal to 0. That is x2 equal to x3. So the values of x2 and x3 are same. We substituting the value of x3 equal to x2 in the second equation. We have a 2x1 plus 5x2 plus x2. We have x3 is same as x2. So you take x3 is equal to x2. We have a 2x1 plus 5x2 plus x2. That is 2x1 plus 6x2 equal to 0. So 2x1 plus 6x2 is equal to 0. That is x1 is equal to minus 3x2. So you're taking x3 equal to 1. Take x3 is equal to 1. We have a x2 is also same as 1. So x3 is equal to 1, x2 is equal to 1, then x1 is minus 3x2, x2 is 1, we have x1 is minus 3. So the eigenvector is x1, x2, x3. Transpose is equal to minus 3, x1 is minus 3 and x2 is 1, x3 is 1. So minus 3, 1, 1. So the eigenvector for lambda equal to minus 1 is minus 3, 1, 1. Now we find the eigenvector for lambda equal to 3, the second eigenvalue lambda equal to 3. So for finding the eigenvector for lambda equal to 3, we again substituting the value of lambda equal to 3 in the characteristic matrix. Then the matrix becomes minus 4, 2, minus 2, 2, 1, 1, 2, 1, 1. Okay, this matrix is obtained by substituting the value of lambda equal to 3 in the characteristic matrix between A minus lambda I. That is, the matrix is minus 4, 2, minus 2, 2, 1, 1, 2, 1, 1 into x1, x2, x3 equal to 0, 0, 0. So the equations are minus 4x1 plus 2x2 minus 2x3 is equal to 0. 2x1 plus x2 plus x3 is equal to 0. 2x1 plus x2 plus x3 is equal to 0. These are the three equations for this matrix form. But here the last two equations are same, since the vectors are, the row vectors are linearly dependent. So for finding the eigenvectors or finding the values of x1, x2 and x3, we excluding the last equation. That is, we take the first two equations for finding the eigenvector for lambda equal to 3. The last equation is depending on the second equation. So from the first two equation, we have a x1 is 2 into 1. 2 into 1 is 2 minus 1 into minus 2 is minus 2. That is 2 minus minus 2 is 2 plus 2 is equal to 4. x1 by 4 equal to, we have second, we have one minus here. So minus x2 by, for x2 we have taking x1 and x3 column. So x2 we have a minus 4 into 1, minus 4 minus 2 into minus 2. So minus 4 into 1 is minus 4 minus 2 into minus 2. Minus 4 plus 4. Minus 4 plus 4 is 0 here. So here 0. So we deleting that minus in x2 here. Okay. So for x3 you taking x1 and x2 column. For x1 column we have a minus 4 into 1. So minus 4 into 1 is minus 4 minus 2 into minus 2. That is minus 4 is minus 8. So x1 by 4, x2 is x2 by 0, x3 equal to minus 8. This 4 is a common factor for these values. So you are dividing throughout with 4. We have the eigenvectors are x1 is equal to 1, x2 equal to 0 and x3 is equal to minus 2. The eigenvector for lambda equal to 3 is x1, x2, x3 is equal to 1, 0, minus 2. Now we find the eigenvector for the next eigenvalue lambda equal to 5. So similarly, we substituting lambda equal to 5 in the characteristic matrix A minus lambda I. The matrix is the matrix obtained when substituting lambda equal to 5 in the characteristic matrix. We have a minus 6, 2, minus 2, 2, minus 1, 1, 2, 1, minus 1 into x1, x2, x3 equal to 0, 0, 0. So the equations are minus 6x1 plus 2x2 minus 2x3 equal to 0. 2x1 minus x2 plus x3 is equal to 0. 2x1 plus x2 minus x3 is equal to 0. Then you calculate the eigenvectors from these equations. So here also, here we have 3 different equations. So for x1 we have a 1 into 1 is 1, minus 1 into minus 1. So minus 1 into minus 1 is 1, minus 1 into 1. So 1 minus 1 is 0 equal to minus x2 by x2 we have a 2 into minus 1, minus 2 minus 2 into 1. So minus 2 into 1 is minus 2. x2 by we have a, so here it is a minus 4. So we have a minus 4 here. We have a minus 4 here. So we have a minus 4 here. X2 by 2 into minus 1 is minus 2. Minus 2 into 1 is minus 4. Also x3 by we have a 2 into 1 is 2 minus 2 minus 2 is 2 plus 2 is equal to, here also we have a 4. Okay. So for x1 we have a, we avoid the first row and first column. We have a, for x1 we have a minus 1 into minus 1 is 1, minus 1 into 1 is, so 1 minus 1 is 0. For x2 we put on minus here, so minus x2, we avoid the first row and second column. So the balance is 2 into minus 1. 2 into minus 1 is minus 2, minus 2 into 1. Oh, minus 2 is minus 4. For x3 we have a x3 we have a 2 into 1. 2 into 1 is 2, minus 2 into minus 1 is 2 minus minus 2 is again 4. So we have here minus 4 and 4. Minus 4 and 4 here. Minus 4 and 4. So the eigenvectors are, if we are dividing throughout with 4, we have the eigenvectors are 0, 1, 1. So the eigenvector for lambda equal to 5 is 0, 1, 1. Now we form the model matrix X as the column vectors are the eigenvectors. So the eigenvector for the first eigenvector is, we got the first eigenvector as minus 3, 1, 1, and the next eigenvector is 1, 0, minus 2, and the next eigenvector is 0, 1, 1. So we write the model matrix X as the eigenvectors are the column vectors, that is minus 3, 1, 1, 1, 0, minus 2, 0, 1, 1. Now we need to find the inverse of this matrix X. For finding the inverse, you take the adjoint by determinant. The determinant of this matrix is minus 3 into minus 2 is minus 6. So 1 into 0 and the last entry is 0. So the determinant is minus 6. So we have 1 by minus 6 into cofactor of this matrix. That is for minus 3, the cofactor is 2, then 0, minus 2, minus 1, minus 3, minus 5, 1, 3, minus 1 transpose. That is 1 by 6 into minus 2, 0, 2, 1, 3, 5, 1, minus 1, minus 3, 1 is the inverse of this matrix X. So for diagonalizing, next we take the product X inverse AX. So X inverse AX is 1 by 6 into X inverse is minus 2, 1, minus 1, 0, 3, minus 3, 2, 5, 1. Into A is our given matrix, minus 1, 2, minus 2, 2, 4, 1, 2, 1, 4. Into our X is minus 3, 1, 0, 1, 0, 1, 1, minus 2, 1. And then you take the product. We have a 1 by 6 into, the first matrix is minus 2, 1, minus 1, 0, 3, minus 3, 2, 5, 1 into product. Product is minus 1 into minus 3 is 3 plus 2 minus 2, that is 3. Minus 1 into 1 is minus 1 plus 4 is 3. Minus 1 to 0, 0. 2 into 1, 2 minus 2 is 0. 2 into minus 3 is minus 6 plus 4 plus 1. That is minus 1. 2 into 1 is 2, minus 2 is 0. 2 into 0, 0. 4 into 1, 4, plus 1 is 5. 2 into minus 3 is minus 6, plus 1 is minus 1 plus 4. So minus 6 plus 5 is minus 1. 2 into 1 is 2, minus 8. So minus 6. 2 into 0, 0. 1 into 1, 1. 4 into 1 is 5. 4 into 1, 4. So 1 plus 4 is 5. That is 1 by 6 into, then you again take the product of this matrix. We have a minus 6, 0, 0, 0, 18, 0, 0, 0, 30. That is, we divide the 6, we have a minus 1, 0, 0, 0, 3, 0, 0, 0, 5, which is a diagonal matrix with the diagonal entries are eigenvalues. Our eigenvalues of the matrix are minus 1, 3, 5. So in this diagonal matrix, the diagonal entries are eigenvalues. So here the first eigenvalue is minus 1, that corresponding to the first column vector. Here minus 3, 1, 1 is the column vector corresponding to the eigenvalue minus 1. 1, 0, minus 2 is the column vector corresponding to the eigenvector corresponding to the eigenvalue 3. And the 0, 1, 1 is the eigenvector corresponding to the eigenvalue 5. So the diagonal matrix of our matrix A is minus 1, 0, 0, 0, 3, 0, 0, 0, 5.